Hi friends, welcome to follow up. Let's have a look at problem 2653, sliding subarray beauty. This is a newly appeared problem, and in this video we're going to expose to you a solution which is time limited, and then we optimize it a little bit to make it pass all the test cases. So essentially, due to the problem here, so we are using a sliding window, but we need to pay attention to the coding efficiency or the time complexity for this problem. So now let's have a look at the main statement. So here we are given an integer array called nums containing n integers. We want to find the beauty of each subarray of size k. So first, it's a very simple fact to compute that there are n minus k plus 1 length k subarrays. Here, the beauty of a subarray is defined in the second paragraph. So actually, it takes me several extra seconds to digest the definition. So the beauty of a subarray is the x smallest integer in the subarray if it's negative, or 0 if there are fewer than x negative integers. So here, if you just look at this paragraph from the very beginning up to now, so you actually might be confusing. But here, actually, x is a given integer or given counting, right? So we are going to consider the x smallest integer. So as such, we need x to be less than or equal to k, right? So which is specified here in the additional assumption or constraints. Here we want to return an integer array containing n minus k plus 1 integers. So this number actually is the number of length k subarrays. So which denotes the beauty of the subarrays in order from the first index in the array, right? So here it also explains a subarray is a contiguous non-empty sequence of elements within an array. So to be frank, I feel that the statement of this problem is sort of not very clean in some sense, especially in the definition of beauty, right? And also this one and this part. But you know, we can use these examples to digest what's intended in this problem statement. So in the first example, k equals 3, right? So we want to consider length 3 subarrays, and we want to consider the second smallest integer. So if we look at the first subarray, so that's the 1, negative 3. So the second smallest one will be negative 1, right? So because we want to consider the x smallest integer, some sort of ordering should be invoked in the coding part, right? So if we sliding window to the next subarray of length 3, so we look at the second smallest integer, so it would be negative 2, right? And if we look at another length k subarray, so the second smallest one will be negative 2. But in this example, the cases are that all the corresponding second smallest elements are negative. Actually, if they are positive, so we need to choose make it to be 0. In other words, we want to consider the minimum of 0 or the x smallest integer in the subarray. So that's the definition of beauty, right? So let me write it here. So what's the beauty, right? The beauty of a length k subarray. So this is nothing but min of 0, and if we have already make this subarray sorted, so and then this will be the sorted array. If we sort from small to large, so the x smallest one will correspond to index k minus 1. So this is the definition of the beauty, right? So this is the definition. So we just summarize it a little bit. So this is actually very neat However, this sentence, I feel that it's not very clear. So now with that said, basically let's look at example 2. So here we have length k is 2, right? We want to consider length 2 subarray. So here we have -1, -2. So the second smallest one will be -2. So similarly, you can consider -2, -3, and -3, -4, right? -5 and -4 and -5. So all the things, the corresponding second smallest one are negatives. But if you look at the third example, so if you look at the first one, so you get this one. So -3 and 1. So the first smallest one is -3, so it's negative. But if you look at 1 and 2, so they are all positive. So we need to pick 0. So that's the thing here, right? So this is what we want to emphasize. So now with that done, basically we have the constraints. So here n is the length of this list, and n can be as long as to 10 to the power 5. So this is so the third one and the fourth one are basically consistency assumptions, and the last one is on the element range, right? So this is not that essential, right? So with that done, basically we can talk about our plan. So first I'm going to make an implementation using binary search. See the bisect module or library. So this actually will help us digest the procedure. So if we test that, it match got time limited error, and then we are going to do a slightly optimization using sorted containers. So actually, this sorted containers can be very useful. You can use it, like say in the leetcode problem solving, or you can use it in your daily work. So with that done, finished said, let's look at the coding part. So for the coding part, I'm going to initialize a result variable. So this variable is going to hold the beauty for the subarrays. Its length is going to be n-k+1. So here, let's see, just for convenience, we introduce this n. N is nothing but the length of this nums. So first, I'm going to check the one of the length k subarrays, so ending at index k-1. So from 0 up to index k-1, there are k elements, right? So we're going to sort this one. The reason is that we want to find the x smallest one, right? So in this case, because we have retrieved that, or we have isolated that the beauty of length k subarray is nothing but the minimum of 0 and the k-1 smallest number in the array, right? So if we do the sort, and then we just need to retrieve the element at k-1. So after we do this sort, what we do is we append. So we append the beauty. The beauty is nothing but minimum 0 and current k-1 x-1. So here I think I need to update this. This is the x, right, not case, right? So here x-1 and 0. So this one we finished the first subarray. Then we're going to iterate, right, for I in range. So from index k up to index n-1. So we write n here. First, we want to take nums I into consideration and remove nums I minus k. At the very beginning, if the index is k, we just need to remove the 0th element, right? So let's do this. We do remove, right, nums 0, right? So after we do that, we need to insert the current nums I into the correct position in the current. So for this, we can do two things. We can use insert, or we can just use bisect to get the ID, then do the insertion. So let's first use the bisect. So here we can use bisect left, it does not matter, right? So current and nums I. So we want to find, if we want to insert nums I into current, because current is originally sorted. After we remove one element, it's still in a sorted order. So we can do this. Then let's check if IDX, because after we remove one element in current, its length will be k minus 1, right? So if IDX equals k minus 1, it means that all the element is less than this nums. So we just need to do current append, right? Nums 9. So this operation is just O1 because this, but otherwise, so we need to do an insertion. So so insert. So we're going to insert it at this index, right? And then nums I. But this operation is expensive, right? Basically, it's O of k. So now after we do this, what we do is to append the current beauty. That's nothing but min 0 and the current x minus 1, right? And then after we finish this for loop, we finish the problem logic, and then we can do return. So we just need to return the result state. So let's first do a check. Here list removes let's see where I remove x not in list. So let's see, not remove remove 0, removes I minus k, right? So if I equals k, it will be num 0. Now let's do a check. Yeah, it passes the first example. Now let's look at the second example. So here the first line is a list, and both k and x are 2's. So now let's check. Yeah, it passes the second example. So now let's check the generic case. So actually, if here we check the generic case, we might find that we get time limit exceeded, right? Let's wait and see. Yeah, we get time limited. Actually, it passes most of them. There are several of the test cases cannot pass. I guess mainly the thing is that this part, this insertion, this is an expensive operation. A relative, I would say. So we want to improve this slightly. So before we make the use of sorted containers, let me comment on this part. So this part, do this, right? So this actually corresponds to do insert, right? Bisect, insert left. So we're going to, this is what we want to insert. The number we want to insert is nums I. So this plays the same role. If you test the special cases, it still pass, and if you test the generic case, it's still time limited. There are 6 or 7 examples that are time limited out of the 720 or test cases overall. So that's the current state. So here, basically, again, this is the insert operation, which uses more time. So now let's improve this a little bit to make it make the work done. So in order to do this, I'm going to use sorted containers. So let me copy this class and function signature and put it here. And then I'm going to change this one to be solution v1. So here I'm going to use a sorted container. So I'm going to use a sorted list. So basically, you can first make a import from sorted containers. Sorted containers import. We can use a sorted list. So the sorted list will maintain this list in a sorted order. So this way, it helps us to retrieve this elements. So for example, you want to choose the second smallest or fifth smallest, or in general the x smallest element. That will be easy. So now let's do the job first. So here what we do is let's use a sorted container, right? So here I'm going to sorted list. So first, parallel in the first solution, I'm going to use the first key elements. Then we do a type conversion. We make this one a sorted list. And then we want to do the result. We append, right? So let's first initialize that like this: a min and 0, a sorted container, right? The x minus 1 elements. So now the result have 1 element, right? So now what we want to do is the sliding window part, right? So for the sliding window, essentially we are doing the same thing here, right? So for I in range k and to m, right? So what we are going to do is that we are going to add this. Let's first do remove maybe. So let's remove nums I minus k, right? And then we sorted container, we add this nums I, right? So in other words, we pop or remove the oldest one, and then as the current nums I we are looking at, right? And then we get a updated sorted container. So we want to append the beauty for this one, that is min of 0 and sorted container at x minus 1. Now we actually just need to do the return. So actually from this piece of code you may find that so once we digest the logic, so actually for the coding part, so it can be very short, right? So now let's first do a test for the 2 example cases to see if we can pass that. Then we do a generic case check. This is not let's see, SR TD, right? SRTD. And yeah, so let's write it to be length nums. Yeah, it passes one example, right? So now let's look at this one, just to make it safe before we do a generic case test. So you get 3 for the subarray length, and we want to consider the second smallest one. Yeah, it passes also the example 1. Now let's look at the generic case. Yeah, it passes all the generic cases. So I would say this is just one way of doing this problem. With more effort, so we can come up with other formats of solutions. But basically, the idea is like this. So you are welcome to modify or comment and come up with other formats of solutions. With that said, I guess that's about it for this video. And if you found this explanation of use, you can follow me up in my YouTube channel. Thank you.